This is some work we've done recently. The abstract was submitted by Eugene Ivanov. I think somewhere in the proceedings, Michael Tobar was listed as the presenter. I guess by process of elimination, I am Stephen Parker, and I'll be talking about what we've been doing recently. And the broad sort of motivating question behind this work is, what is the lowest power signal that we can confidently detect using our existing hemp-based low noise amplifiers, either at room temperature or at cryogenic temperatures? And so what I'm going to do is I'll provide sort of a minimum level of context behind our application, which is experimental searches for dark matter axions. And then I'll provide a selection of comments, simulations, and experimental measurements of the detection of signals that sort of range from monochromatic to pseudo-monochromatic and slightly more broadened. And then at the end, I'll also talk a little bit about a more specific multi-channel cross-spectral readout system, which we've done a little bit of work on. So axions are a proposed type of particle that could exist, and if they do exist, they could also be a component of dark matter. And what's important here for our purposes is there's lots of different ways that you can try and detect axions, and one of the nicest, most model-independent ways that you can do this is to look at the coupling between the axion and photons. And that's the approach that we take. And so you have minimal model dependence when you do this, and the important point is you have an axion of some mass, it's a very low mass particle, and you use an external magnetic field to act as this second photon or virtual photon in this process, and you create a real photon, and the mass of the axion will dictate the frequency of the photon that is produced. And the regions of interest sort of end up covering photons in the RF, microwave, and millimeter wave spectrum. And so what we're going to do is we're going to try and look for signals, microwave signals, and from the level of power detected, try and constrain the strength of the coupling between axions and photons. Now, the properties of the expected signal aren't entirely clear. They're not 100% defined. There's different models will give different predictions, so we need to have some flexibility in how we're going to process our data and look for detection. And so this is an overview of sort of the experimental system that you would use to do this kind of an experimental search, where you have some external magnetic field and you apply this over a resonant cavity, so that when your axions convert into photons, you can sort of resonantly enhance the signal, and then you will read this out with some sort of chain of amplifiers and do direct sampling or some sort of down conversion depending on what frequency range you're looking at. And you can have some estimate of the amount of power you would expect to be converted due to axions, and this will come down to, say, the local density and some other experimental parameters. So as I said before, we want to measure power to constrain axion-photon coupling. And the origin of the axions, be they different models of dark matter, different forms of dark matter, or maybe even not dark matter at all, this will sort of dictate some of the behavior of your expected signal. And if you're looking for some more in-depth information regarding haloscopes, there's a paper there, or more information regarding the coupling between axion and photons, there's a recent paper we just produced down the bottom as well. So more specific to our experiment that we're looking at doing, we would operate at cryogenic temperatures. You reduce your noise background that you're trying to resolve above. And in our case, we're going to be using hemp-based LNAs. And so we can safely assume that we have a situation where the temperature of our resonator is substantially lower than the effective noise temperature of our amplifier. We'll be cooling our resonator down to millikelvin temperatures, while the amplifier will be anchored at 4 Kelvin with a similar level of noise temperature. And we can consider the power spectral densities of the different components that we're going to be looking at here, and we have a choice to make about whether or not we want to include some sort of circulator or isolator in between the resonator and the amplifier. If we just connect directly, we can see this contribution due to the thermal noise of the cavity, and on resonance we'll have back absorption of the technical noise of the amplifier, and so we'll see some combined spectrum here. If we have a circulator in line, we won't see this level of back absorption here, and we can define sort of an idealized figure of merit here, which is the ratio of the spectral density of our desired signal that we want to characterize over the sum of the spectral densities of our different noise sources. This isn't really entirely practical for real signals, as we will see. It turns out, though, if you just look at these functions here, which are from this idealized signal-to-noise ratio, and you plot them, if you're critically coupled, it's essentially the same sensitivity between the two systems. So we don't need to worry too much about this. Now I'll move on to talk a little bit about some of our simulation work. This is the basic concept for our approach. We'll be looking at both single and dual channel systems here. And so we start with some signal of interest, which will be coherent and correlated between however many channels we decide to look at, typically 2. And then we introduce unrelated noise processes and feed this into our signal processing system here. And we're going to be digitizing or looking at discrete signals, and we can then compute the cross-correlation or autocorrelation functions, and from this determine the power spectral densities. And so this is kind of the workflow that we have in Mathematica, where you start with the signals, you do some sampling or digitization, you pad it out, do your correlations, and then you can compute your spectral densities as such. So this might be an example of what an experimental setup could look like, but at least for our simulation work and also for experiment, we want to have some level of flexibility. So let's say we have these 2 separate resonator amplifier systems. They're mixed down, filtered, sampled, and then we go into our system. And we can process our data in a number of different ways. We can look at long samples with a few averages, or we can cut it up into smaller observation lengths and do lots of averaging, depending on what sort of signal we might be searching for. So now it's probably a good idea to define our signal-to-noise ratio for, let's start with monochromatic signals, where most of the power is in sort of a narrow frequency bin. And what we will look at is the maximum value of the power spectral density here at the signal. We subtract the mean of the white noise away from this peak, and then we refer this to the standard deviation of this white noise distribution here. We could use any other type of noise process and actually just look at the bits from a residual to make it white, but for simplicity, we'll be dealing with a white noise background. And here's an example of some of the simulation data. This would be a single channel trace here, and then this would be the cross power spectral density between 2 channels. And this mean level of the white noise is simply suppressed by the square root of the number of averages. Meanwhile, if you look at the variance or the standard deviation of this white noise in the cross spectral density, it's half of what you see in the single channel, and the single channel scales down with square root number of averages. And so if we consider the difference between taking long observation times and a smaller number of averages, or shorter observation times and a lot of averages, we can plot this out here, and it shouldn't be too surprising if you're dealing with a monochromatic signal. It's more advantageous to measure for as long as possible. I'd have a very, very small resolution bandwidth for your spectrums and minimize the number of averages you take. And so we can sort of recreate this experimentally as well, where we have 2 synthesizers, both referenced, and we use one just as on the LO of a mixer. We can attenuate heavily our signal from here, and we're going to look at the very, very weak beat note signal between these 2 synthesizers. Powers on the order of initially, say, 10 to the minus 22 watts. And we'll need to get sort of preamplifier, and then we're just doing a very simple digitizing and analysis afterwards. And we need to, first of all, make sure that our beat note doesn't interfere or fall where there's sources of noise, primarily mains harmonics. So in between these spurs, we can place our beat note right here. And so, for example, this is the same number of data points, just dealt with in different ways. We have a larger resolution bandwidth here, meaning we're taking lots of averages of shorter sets, and the opposite case here, where we're taking lots of a few longer sets and then averaging those. We see that we have a higher signal-to-noise ratio in this case. We can compare that to what we might expect to see, and the value of the signal is fairly close. There's a bit of a discrepancy. This mainly comes from ambiguity in correctly characterizing the conversion efficiency of the mixes. And we can extrapolate these room temperature results that are on the order of 10 to the minus 21 watts down to 4 Kelvin, and expect that this same parameters would allow us to detect something on the order of 10 to the minus 23 watts. And we can repeat the measurement again at a lower level of power, see very similar sort of results, and extrapolate down to expect to be able to detect powers on the order of 10 to the minus 24 watts at cryogenic temperatures. If we start to broaden our signal and it becomes more of a pseudo-monochromatic signal, we can introduce some random walk of phase here. For a set signal duration, we'll see that, as one might expect, this sort of smears out the energy of the signal, the broadening of the power spectral density. And what this means is that your strategy of observing for a long time and creating limited averages is less effective as you start to broaden out the signal, and it becomes, the line width of the signal becomes comparable or even greater than the resolution bandwidth. Your ability to resolve the signal is decreased, and you have your signal to noise ratio really just scaling with the square root of the number of averages. And this is another sort of look at this. Down here, we have the line width of the signal as it transitions from a noiseless signal to much more of a broad and noisy signal. The total number of data points in your data file required to resolve a signal with a signal to noise ratio of 5. You can see for a noiseless signal, you want to have a very low resolution, and then as it becomes noisier, you just want to broaden this out quite a bit. If your signal becomes too broad, you might want to take a different approach to the analysis, which is where you look at an integral of the power in some region of interest, and you can then compare this to a detuned integral far away from where you expect your signal might be. And as you broaden out this integration band here, you start to absorb or benefit from more and more power from the signal. And once you're over about 15 times the line width of your signal, you seem to have saturated with the maximum amount of useful information. And you can do this sort of processing for signal to noise ratio in simulations, where you look at the power where your signal should be, and you find you have most of the power here, and then you compare it to the detuned information there. And this is just an example of some simulated spectra using that sort of approach. And what we find here is if you look at the ratio of the integration window for this calculation over the resonator line width, as you increase this, you start to extract more and more useful information, more power, and this also helps out with your signal to noise ratio. And so, for example, for quite a broad signal, we expect to be able to resolve on the order of 10 to the minus 22 watts at cryogenic temperatures. Now, what I'd like to talk a little bit about is sort of a more specific readout mechanism for our experiment, which is scaling up to a multi-channel or an M-channel cross-correlation readout, where instead of having 2 channels, we're going to look at some larger number of cavities. And this is different to say, a little bit different to normal applications using cross-correlation, where our power from our signal hasn't actually been split at all. Because we're using separate cavities, they each produce the same amount of power, and they each form an independent measurement arm here. And what we can do is we can compute the cross spectrum. We digitize all, say for example, 4 systems. We can compute quite a few different combinations of these cavities, M take 1 on 2, so we have 6 different unique combinations of these cross spectrums. And what we can do is we can compute each cross spectrum, and then we can just take the average of all these cross power spectral densities. And what we expect to happen is that the standard deviation for the noise in the average cross spectrum should be suppressed by this factor here compared to a single channel. And if you have 4 cavities, that's about a factor of 5. So we can do some simulation work to demonstrate this. Here's the power spectral density for a single channel after a set number of averaging with white noise background, and again, a monochromatic signal placed in the middle here. Now, if we look at the cross spectrum between any 2 channels, it looks a little bit like this, where the mean has been pushed down with your averaging. And then if we compare this to the average of the 6 cross spectral pairs, we see that basically the error or the deviation of the cross spectrum has been reduced down in the average, as you may expect. And you can do the same thing also again with slightly broadened signals and observe very similar type of results. And if we look at the signal to noise ratios for these different systems, again using this monochromatic expression for signal-to-noise ratio. In a single channel, we have this scaling with root m. Then in the cross-spectral density, you have this factor of 2 improvement. And then once you have your multiple channels, you get this root 6 from the number of combinations. And so we do see that the deviation has been suppressed by this factor here. And you can sort of look behind these different components and observe things that you might expect to happen. In a single channel, you have a constant mean with a reduction in standard deviation as you average. You have this reduction, root m reduction in the cross-spectral density with this factor of 2 for the standard deviation. And then you have this root 6 further reduction in the cross-spectral density when it comes to the standard deviation. So, in summary, we can relatively confidently detect quite low levels of power using hemp-based LNAs, and we have the possibility to further improve sensitivity using multi-channel cross-spectral readouts. Thank you.